Hello everyone, today let us discuss about AC voltage applied to a series LCR circuit. LCR means L stands for inductor and C stands for capacitor and R stands for resistor. So three of them are connected in series and AC voltage is applied to that. And already I told you in my previous videos, for every circuit we need to find the equations of 5 quantities. Already I told you, that is number 1 voltage equation, number 2 current equation, number 3 resistance of the circuit, that is called as reactance in some circuits, and impedance in LCR circuit. Number 4 phase difference between voltage and current, and number 5 power of the circuit. And for every circuit, already I told you, we need to draw 3 diagrams, 3 figures. The first one is circuit diagram, and the second one is wave diagram, and the third one is phasor diagram. Okay, now we have to find the equations for all of them. For voltage we need not find anything because already it is given for everything as a common equation. So for voltage we know the equation V is equal to Vm sine omega t. It is a common equation for all the circuits which we have derived from the AC generator. Now the circuit diagram goes like this. First we have to draw the circuit diagram. Just AC voltage applied to resistance. So let us take a resistance here and let us take a resistance here, and then it is applied to a capacitor. So you can take a capacitor here and then an inductor. This is the inductor. So 3 are connected in series. This is resistance, this is capacitor, this is inductor. Now this is the AC voltage, which is the EMF, or we call it as the AC source supply. Now we have seen the voltage equation. V is equal to Vm sine omega t, and we have to go for the remaining equations. Then what is the phase difference between voltage and current? We don't know. So we assume, this is only our assumption, we assume that there is a phase difference of phi between voltage and current. This is only our assumption. At the end we will see what is phi now. Initially we don't know what is the phase difference. So let us assume, let phi be the phase difference. Okay, let us assume that is phi be the phase difference between voltage and current. Okay, between voltage and current. Therefore, this is our assumption only, as I told you. Let us take the equation of the current. I is equal to Im sine omega t plus phi. What is phi? We don't know. At the end of the discussion, we will come to know what is phi. Let it be equation number 2, where phi is the phase difference between voltage and current. Okay, so this is the phase difference between voltage across the source and the current in the circuit. One more thing I want to tell you, because it is a series circuit, current is same through all the devices. That is, current through inductance and current through capacitance and the current through resistance is same because they are in series. Okay, we have 2 methods to find the equations of all these things. One is an analytical method, which is in the deleted portion. Therefore, we have to go for the second option, that is the phasor diagram. So let us construct first one phasor diagram. Okay. So let us take a phasor diagram. Now let us say this is x-axis and this is y-axis. Okay. Now listen very carefully. Here I am giving you the most important point. In the case of resistance, voltage across the resistance and current through the resistance are in same phase. Okay, you know that. In the case of inductor, that is voltage across the inductor leads the current by 90 degrees, that is by pi by 2. Then in case of capacitor, voltage across the capacitor lags behind the current by pi by 2. Now listen carefully. Let us take current vector first, like this. Because current is common to all of them, this is the current vector. Now, as per the first point, voltage across the resistance and the current are in same phase. That means voltage across the resistance is along this same vector like this, which is VR, and it makes an angle with the x-axis, that is omega t plus phi as per the above equation 2, because current is making an angle omega t plus phi with respect to x-axis, and voltage across the resistance and the current are in same phase. Now let us go for the next one, that is voltage across the inductance leads the current by pi by 2. So you can take the voltage across the inductance like this VL, because the difference between voltage and the current in inductor circuit is 90 degrees. So this is pi by 2 or 90. And in the case of capacitive circuit, what is happening now? Voltage lags behind the current by pi by 2. Therefore, let us take voltage across the capacitor behind the current by pi by 2. Current is this blue line. So behind that it is pi by 2, that is voltage across the capacitor. This is the initial phasor diagram which we have constructed. Now very clearly you see here, I is the current which is common to all because they are in series. It is a series circuit. And then in the case of resistance, voltage and current are in same phase. Therefore VR comes on I line only. But in the case of inductance, voltage across the inductance leads the current by 90 degrees, so it is taken with the light green color. In the case of capacitance, voltage lags behind the current by pi by 2, so I have taken it behind the current. Now, in the case of capacitance, the voltage lags behind the current by 90 degrees, that is shown by the purple color. Okay. Now let us reconstruct this diagram again. So you can clearly see VL if it is like this, and VL is like this and VC is like this. The angle between them is 180 degrees. Just I am giving you example. Now in case of our vectors, if A bar is one side, B bar is on the other side, we take the resultant vector as A bar minus B bar in our vector algebra. In the same way, VL and VC are separated by 180 degrees because 90 plus 90. Then you can take a common vector by combining both of them, and we can reconstruct the circuit again. Okay, we will reconstruct the circuit again. So shall we start? So let us do it very carefully. Now I'll draw it here just for your reference. This is the current. This is the voltage across resistance, and this is the voltage across inductance, and this is the voltage across capacitance. Now we want to combine both of them. So if you take vector form, here they are using capital letters for vectors. That is VL bar is the voltage across inductance. VR bar is the voltage across resistance. So VL bar is the voltage across inductance. VR bar is the voltage across resistance. VC bar is the voltage across capacitance. And V represents the applied voltage in the vector form. Okay. Now let us combine them together and redraw. Now I will redraw this now. Now voltage across capacitance and inductance together I have combined. I am drawing like this. That is, in vector form you can write VC bar plus VL bar. Okay. Even if you don't write minus symbol here, no need, because we have taken as vector form. In case of vector form, automatically when you are substituting the values, we will take negative only. Then after that, we have the current or the voltage across the resistance like this. This is VR, and VR makes an angle omega t plus phi with x-axis. Okay. Then applied voltage makes an angle omega t with respect to x-axis. So let us take the applied voltage, which makes an angle omega t with respect to x-axis. Now you can construct a parallelogram like this. Okay. Now the resultant of VR, VC, VL is V. So that is what we have here. Now in a parallelogram law of vector addition, you know, if you take two vectors A bar and B bar, parallel to A bar you draw one line from B, and parallel to B bar from A you draw one line, and then you join the diagonal. The diagonal gives A plus B. That is parallelogram law of vector addition, which comes in our 11th standard. In the same way here, VR is one side of the parallelogram, VC plus VL is the another side of the parallelogram. Therefore, you can write now V bar is equal to, that is VL bar plus VR bar plus VC bar. Okay, let it be equation number 3 according to me. Now I will write voltage across the resistance VRM is equal to IM into R. Voltage across the capacitance VCM is equal to IM into XC. Voltage across the inductance VLM is equal to IM into XL, where X is the capacitive reactance, IM XL, where XC and XL are the capacitive and inductive reactances. So as you know, X is the capacitive reactance and XL is the inductive reactance. Okay. Now this is the vector form. Equation 3 is a vector form. Now in magnitude form, if we write them, you will get now in magnitude form voltage across the inductance plus voltage across the resistance plus voltage across the capacitance is equal to V. Let it be equation number 5. Okay. Now what we have to do now, if you see these equations, what we understand that VCM minus VLM with modulus, that is magnitude of maximum voltage across capacitance and magnitude of voltage across inductance, that is nothing but in the vector form we write it as VC plus VL bar. So in the vector form you have to write like this, but whereas in the magnitude form you have to use minus. Magnitude means we are taking values, but in vector form you can write a plus. Okay. Now VC and VL, they become one side of the parallelogram. I'll take you up and show you here. VC and VL, which is shown by the purple color in this diagram. So you can see here, this is the diagram I'm talking about now. Here, this is the diagram. Okay, I'll give this is diagram number 1, this is diagram number 2. Then if you see in the diagram number 2, you can see VC plus VL is the one side of the parallelogram and VR is the another side of the parallelogram. Therefore, taking the magnitude form, you will get now. So, let us apply that Pythagoras theorem here. You can see here Pythagoras theorem, if you apply, this becomes a right angle triangle like this. So, where this V becomes the hypotenuse, VR is one side, VC plus VL is another side. So you can clearly show that this one is hypotenuse, V is a hypotenuse, that is equal to V square is equal to VR square plus VC plus VL whole square. Okay, so with that I will write now, that is Vm square is equal to Vrm square plus VCm minus VLm whole square. Okay. So let it be equation number 6. Here I have used Pythagoras theorem. Therefore, Vm square is equal to Vrm from, if you go up and see from equation 4, Vrm is Imr, SCM is Imxc, VLm is equal to Imxl. Okay. So let us substitute equation 4 in equation 6. Okay. I will write now. Equation 4 in equations 4 in equation 6, Vm square is equal to Imr whole square plus Imxc minus Imxl whole square. So you can take out Im square common, it will become R square plus Xc minus Xl whole square. This is Vm square. Actually we are going to derive the expression for current. Therefore you will get now Im square is equal to Vm square divided by R square plus Xc minus Xl whole square. Therefore Im is equal to under root Vm square divided by R square plus Xc minus Xl whole square. So you can compare it with the Ohm's law. Then you will get here, Im is equal to Vm divided by under root R square plus Xc minus Xl whole square. So let it be equation number 7. Equation number 7. Okay. Now if you compare it with Ohm's law, so you know Ohm's law, V is equal to IR or I is equal to V by R. So in place of I you have Im, in place of V you have Vm, and in place of R you have all this quantity. Therefore that quantity is the resistance of the circuit, but here we don't call it as the resistance, we call it as the impedance of the circuit. So impedance of the circuit is given by the letter Z. Z is equal to under root R square plus Xc minus Xl whole square. Equation number 8. So this is the resistance of the circuit. Okay, so with these values we got resistance value also. And first one is voltage equation, second one is a current equation, and the current equation already we wrote, I is equal to Im sin omega t plus phi we wrote. This Im value we got here in equation number 7. Okay, now after that, what is this phi that we need to know now? Okay, so we need to know the phi value now. I'll take it down. Yes. To know the phi value, let us redraw the triangle like this. One side it was V, another side it was VC plus VL, another side it was VR. So in the same way you can take one side it is VCM minus VLM, another side we have V, another side we have VRM. So this was the triangle which you have above. If you want, I'll take you up once. Yes, this is the triangle I have redrawn. One side is VC plus VL. Because this purple line and the opposite line, they make a parallelogram. Therefore, this is VR, so this will become VC. So this will become VC plus VL. This side will become VC plus VL. So the same thing I have drawn here. You have a right angle 90 degrees. So the same thing I have drawn below, the same triangle. Now if you see here, the other side we have phi, that is the angle. Then you can write tan phi is equal to opposite side, that is VCM minus VLM, divided by adjacent side, that is VRM. Okay, then let it be equation number 9. But if you go up and see, we have VRM, VCM, VLM values are here in equation 4. Substitute them, that is equation 4 in equation 9. You will get now, that is tan phi is equal to VCM, that is VCM, that is IMXC minus IMXL divided by IM into R. So IM is common, XC minus XL divided by IMR. So you can cancel out IM and IM. Then you will get in the next one, that is tan phi is equal to XC minus XL divided by R, equation number 10. Now you also got the phase difference now. So with this phase difference, with that peak value of current, you can know the equation of the current, that is I is equal to Im sin omega t plus phi. Now if you see the current equation already which we wrote, I is equal to Im sin omega t plus phi. In the beginning I told you what is phi, we will come to know at the end of the discussion. Now we came to know the value of phi here, that is tan phi is equal to Xc minus XL by R, or you can also write phi is equal to tan inverse Xc minus XL by R. So this is the equation for the phase difference. Now that phase difference, if you substitute in this current value, you will get the current equation. Now we got almost all the values. Now here one more thing I want to tell you, what is the important point to know. Suppose if XC is greater than XL, we call it as a capacitive dominant circuit, that is circuit is predominantly capacitive. In this case phi becomes positive. Very important point to be noted. But in case XL is greater than XC, we call it as inductive dominant circuit. The circuit is predominantly inductive. In this case, phi becomes negative. So phi becomes negative. So in this case, if XC is greater than XL, current leads. If XL is greater than XC, voltage leads. Which is leading, that depends upon the values of XC and XL. So if XC is greater than XL, it will be current leading circuit. If XL is greater than XC, it will be voltage leading circuit. And the last point we need to know is power. And finally, we need to know the power of the circuit. So just now above we have Im is equal to Vm by Z. And we got phi is equal to tan inverse Xc minus XL divided by R we got. Okay, now let us go for power. P is equal to V into I, that is Vm sine omega t into Im sine omega t plus phi. Okay, then on simplifying using trigonometrical functions, finally we will get Vm Im by 2, then you will get cos phi minus cos 2 omega t plus phi. So this is the equation you get once you simplify. Then what we want is average power. We have done it for all the previous circuits. Okay, average power means what we do, we put a bar for this one and we put this in triangular brackets, and here we have two functions. One is cos phi, another is cos 2 omega t plus phi. In the first function we don't have any term related to t, but in the second one we have omega t. There is a function of time. Whenever there is a function of time, it varies with the time, then it is a cos function, half cycle positive, half cycle negative. On an average, this value becomes a 0 over a full cycle. Therefore, what remains now is P bar is equal to Vm Im by 2 cos phi. So this is the power of the circuit, which is equation number 12. Equation number 12. So now if you see here, we got power P is equal to P bar is equal to, or P is equal to Vm Im by 2 cos phi. Cos phi is called power factor. Another new name you are learning. We have so many numericals in our competitive exams to find out the value of phi. So cos phi is called as the power factor. So they will also ask you to find out cos phi, that is power factor, in our competitive section. So you can also write the power in the AC form. You can also write power in RMS values. Capital P is equal to Vm Im. This 2 I am writing as root 2 into root 2 cos phi. Therefore power is equal to, that is Vrms Irms cos phi. You can also write it as I square z cos phi. So this is the power in the form of RMS values. Then in the case of LCR series circuit, we have already seen in the above, that is phi is equal to tan inverse XC minus XL divided by R. So in this case, it depends upon the value of phi. If phi is a positive or negative, depends on that, we will get what is the power. Okay, power dissipated, it depends upon the value of phi, and phi may be non-zero in RL or RC or RLC circuit, that is LCR series circuit. So power is dissipated only in the resistor. So this is all about the power. Now we got 5 points here, and what else is left now? Wave diagram and the phasor diagram. We have voltage equation, we have current equation, we got resistance, that is impedance of the circuit, we got phase difference, and we also got that is power of the circuit. And finally what is left is the wave diagram and the phasor diagram. So wave diagram we will draw now. So on x-axis we always take omega t, and already I told you the voltage will not change, it will be in the same place all the time. But current is, if it is a capacitive circuit, let us assume, this is only our assumption, if XC is greater than XL, it is a capacitive dominant circuit. In that case, it will be, that is leading by an angle of phi. So it comes like this. It comes like this. Whereas to mark the maximum value of voltage is here, maximum value of current is here, then this is the phase difference phi. Phase difference between both of them. So this is V and this is I. Okay. Now current is leading here by an angle of phi. Now let us go for our phasor diagram. Okay. As I told you, take any point of your choice. So here I am taking, draw straight lines like this, and here wherever it touches voltage axis, from there you draw one straight line, and where it touches current, from there you draw another line. Then voltage, you can draw the phasor like this, which makes an angle omega t1 with x-axis at any instant of time t1, whereas current is leading by an angle phi. So here you can have current vector exactly with this magnitude. It should not cross. So your arrow should be here only, not more than that. So this is I and this is V, and the angle between them is phi, because current is leading the voltage by an angle of phi. So with this we have completely discussed all about our LCR series circuit. Shall we have a revision to get all the equations of voltage, current and everything from the beginning, so that it's a revision for you all. So let's go here. Now this is our first equation, V is equal to Vm sin omega t, the equation of the voltage. Okay, I'll just show you up here what we have to take now: voltage equation, current equation, resistance, phase difference, power, and circuit diagram, wave diagram, phasor diagram. Here already we have done the circuit diagram, and this is equation 1 is the voltage. Now I have to take you to the current equation. Now this is the current equation which we have, and already we have proved what is the phase difference phi. Once you substitute the value of phi and the value of Im, you will get the exact value of current I. And then we need to know the resistance of the circuit. So resistance of the circuit is called as impedance. So here we have the impedance of the circuit, this one, equation 8. And then the next one is phase difference. Equation 10 is the phase difference. And this is the phase difference. And finally, we need to know the power. And this is the power equation. So we'll give one equation number for that. Let us give equation 12 for that. Equation 12 is the power of the circuit. So 5 points are over. And circuit diagram already I have shown you on the top, and the remaining are phasor diagram and wave diagram, which are here. With this we have completely done everything about LCR series circuit. Okay, God bless you all. Do well in the examinations. God bless you all. Let us meet in the next video with some other topic. And we also have to do LR and CR circuits. Okay, God bless you all. All the best for your exams.